Sum number 87, page number 3.54, sum number 87. You have 3 cells of EMF at 2 volt with an internal resistance of 0.05 ohms. Then another battery with 1.8 volts with an internal resistance of 0.7 ohms. Another battery which is 1.5 volts with an internal resistance of 1 ohm. All of them connected to an external resistor 4 ohms, and then to an ammeter. What is the reading on the ammeter? What is the current through the circuit basically. So all the EMFs are in series, so E is equal to E1 plus E2 plus E3, 2 plus 1.8 plus 1.5 is equal to 5.3 because they are connected in series, and only properly it's connected, there is no positive to positive or so. So what about the equivalent resistance? R equivalent of the entire circuit 0.05 plus 0.7 plus 1 plus 4 ohms, equivalent resistance 5.75, and therefore I is equal to E by R equivalent, everybody knows, as 5.3 by 5.75. The answer for this is 0.92 amps is the current that's flowing through. That's fine, but the question is, can you connect this in parallel and hence do this sum? Do you have a formula? No. You have a formula only when 2 batteries are connected in parallel, which is the derivation I asked in the test also. It's I1 and I2, this is E1, this is R1, and E2, this is an R2. E1 R2 plus E2 R1 by R1 plus R2 is the equivalent, provided there are only 2 cells. If there are number of cells, then you can do number of cells with, provided they all have only the constant voltage and the same resistor, because I would have taught you a number of cells in combination of a number of cells, n cells and m rows like this. I would have taught you that theory where it was all E and R, uniform EMF. So therefore I don't have a formula, I only have to do it using loop rule. So wherever the loop rule has to be applicable, do you understand? When you are stuck, you have to do only loop rule. You know the current flowing through comes like this. This is an I1, this is an I2 and an I3, and comes out as I again. So in that case, they have an internal resistance here, internal resistance here, internal resistance, the values being respectively 0.05 and then 0.7 and 1 ohm, and the battery is being 2 volt and this being 1.8 volt and this being 1 ohm, 1.5 volt. So you have to use the loop rule like this. You have an external resistor also connected here as given in the question, which is a 4 ohm resistor, and an ammeter. You can ignore that. Okay, so then you can use this loop rule, you can do this loop rule, you can do outer loop, you can do this outer loop, that is what is inside this area, and you can also do this, then this, like this. You can do many ways and you can solve the sum. So therefore you understand where you have to use loop rule, where you have to use formula. So then let's go to the next question. They have not asked you to do it, they are asking whether you can do it. Yes, you can, provided you use the loop rule formula. So if it is in parallel. Okay, let's go to the next question. As example 89, 2 identical cells. Okay, there is this circuit. This is 17 ohm and this is 17 ohm, both of them in parallel, and here you have a battery, internal resistor, a battery and an internal resistor. Close the circuit, and this is R, and this is 1.5 volts which is the EMF, and this is also 1.5 volts which is the EMF. It's given in the question that 2 identical cells of EMF 1.5 volts each joined in parallel provide supply to an external circuit consisting of 2 resistors of 17 ohms in parallel. A very high resistance voltmeter reads a terminal voltage to be 1.4. Terminal potential difference is V. What is given is E. It's given that the terminal potential difference is 1.4 volts, which will be the same for both. Because the first thing they are connected both are parallel, so the voltage between across them has to be the same, and the terminal potential difference measured by it is only 1.4. You know that if you want to find small r, there is a formula. Small r is equal to capital R into E by V minus 1. So small r is equal to capital R. You should find what is capital R, which is, this is going to be a capital R. It's in parallel. So 17 into 17 by 17 plus 17. When it's parallel, just half of it, right? So just half of it. What is half of 17? which is 8.5 ohms. So then therefore capital R is 8.5. And what is the EMF of the battery? EMF of the battery is 1.5 by the measured voltage is terminal potential difference is 1.4 minus 1. So you do this and you get answer to be 0. See, a lot of people are making mistakes while you're solving this kind of sums. 1.5 minus 1.4 by 1.4. So this is 8.5 into 0.1 by 1.4. Okay, so then therefore this answer would be 0.6 ohms. That will be the internal resistance of each battery here. This is the way you find the internal resistance of the battery. Okay, once but that again will be the equivalent internal resistance, right? What you had got here will be an equivalent internal resistance. This is not R, it's R equivalent, R equivalent. So 1 by R equivalent is, it's 1 by R plus 1 by R. 1 by R plus 1 by R, which is 2 by R, therefore R by 2, so 0.6 by 2. What I have got here is 0.6 ohms. Okay, what is the mistake I am doing? And it's 1 by R plus 1 by R, 2 by R, so I know it's R by 2. Therefore, R equivalent is R by 2. Yeah, but you know that R equivalent itself is 0.6. Therefore, R itself is 1.2. So this is the way you have to find. You have to reconstruct this with one external resistor, which is 8.5 ohm, and then which is connected to two batteries with R and another battery which is 1.5 ohms with R. So that this acts as an external resistor, capital R, and so then small r is equal to capital R, and you're combining. The potential, terminal potential difference measured is 1.4, which is common for this and this. So you can, this is the way to do. It's very complex. Unless you learn this sum, it's very difficult to do this sum. I hope you are clear. So I'm just thinking, is it possible, exploring, is it possible for me to do it any other way? Is it possible to do the sum any other way? That is an external resistance. Small r, if you have to find, you only have to use capital R and E by V minus 1. That's a formula whenever you have to find internal resistance. You know the external resistor, and yeah, that's the only way you can find. So I hope you're clear with the sum. It's very important. It's come for a CBSE question paper, so I hope you're very clear with this. So let's go to another question, which is the 90th question. Two identical cells. Oh, identical. Identical means it can be parallel. There's no problem. The EMF is E and the internal resistance is small r. EMF is E, internal resistance smaller. EMF is E, internal resistance smaller. EMF is E, internal resistance smaller. So all of them are connected like this in parallel. Yeah, it is allowed because they are all having the same EMF, which is externally connected to an external resistor, both of which are parallel, 15 and 15. I would rather make it as a 7.5 and make it one single. This is the question, but I will make the 15 and 15 as one single external resistor with 7.5 and close the circuit so that it's easier for me to do the sum. Okay, so 4 identical cells, each of EMF 2 volts. So everything is 2 volts, 2 volts, 2 volts, and joined in parallel, providing a supply of current to external circuit consisting of two 15 ohm resistor joined in parallel. Yes, I have calculated it to 7.5. The terminal voltage of the cells as read by an ideal voltmeter is V is equal to 1.6 volts. Calculate the internal resistance. Whenever they give you this, best thing to do is small r is equal to, but small r is R equivalent again. It's just not 1, it's R equivalent is what? Capital R into E by V minus 1. So then in that case, a capital R itself is 7.5 and E is 2 and the measured voltage is 1.6 minus 1, and thus you get a R equivalent whose value will be 15 by 8, similar to last sum, and they are all in parallel, 1 by R, 1 by R. So actually 1 by R equivalent is 1 by R plus 1 by R plus 1 by R plus 1 by R, which is 4 by R, or in other words it's R by 4, and that has to be equal to 15 by 8. So it's 7.5 ohms. The same kind of a sum which has been twisted and asked. Okay, so then these patterns, whenever you see, you are supposed to use the formula and treat the external parallel resistors to be a separate capital R. So that's another sum. And next is sum number 91, which is in page number 3.56. Here is the sum. We have a battery. I mean, when I say battery, it's a cell. You have an EMF E1 of 4 volts with an internal resistance 0.5 ohms. Another cell of 8 volts with an internal resistance 1 ohm. And you have a 4.5 ohm resistor, okay, and a 3 ohm resistor. I already did this kind of sum in one of the something similar last video. It's the world's most important format, 6 ohm here and a 4.5 and 3. The moment you see a positive and a positive being connected, the battery, which means one is getting charged by the other. The lower voltage battery is getting charged by the higher voltage battery. So then E1 is getting charged and E2 is discharging. Immediately write, in this case discharging is a normal condition where V is equal to E minus IR, but here it's V is equal to E plus IR when it is charging. That's the condition that you got to remember. Okay, for which in this whole circuit you need an I. The whole point is to get an I. These two are in parallel, 3 and 6 are in parallel. So it's 3 into 6 by 3 plus 6, which is 18 by 9, 9 2s are 18. That 2 and this 4.5 is in series. So 4.5 plus 2, and also this internal resistance 0.5 and 1 ohm. So 6.5 plus 0.5 is 7, 7 plus 1, 8 ohm is the R equivalent of the entire circuit. Okay, and what about the battery? EMF of this is whenever it's positive and positive connected, negative connected, I told you to write E1 minus E2. So E equivalent is just 4 volts, and to find the current is V by R equivalent, so it's 1 by 2, 4 by 8, so 1 by 2. So this is the current which is going to flow through the circuit. Okay, so the 1 by 2 amps is 0.5 amps, which is what is going to flow. Therefore you know that from this, in this circuit, the current is going to be, among these batteries, I is 0.5 amps. Here is 0.5 into internal resistance is again 0.5. The EMF is 4 volts. So then it's they are asking you to find the okay, they are asking you to find calculate the current in each resistance. Okay. Okay, what am I trying to find? I am trying to find the potential, measured potential or terminal potential difference. So V is equal to, let me continue, 4 plus 1 is 5 volt in here. They ask me what is terminal potential difference between this end and this end of this battery. V is equal to E minus AR. So V is equal to E is 8 volt battery minus I is something that we found out to be again 0.5. The small r is just 1 ohm. So 8 minus 0.5, therefore it's 7.5 is the terminal potential difference. What is given 8 volt and 4 volt are the EMF. What we have found is the terminal potential difference across this cell and across this cell. Okay, and so you found the terminal potential difference to be this if they ask you. Now they are asking for the current through each resistor. Okay, through each resistor. Okay, you got the current to be so you know through each resistor, through the battery you know the current is just 0.5 amps, that is sorted. Through the 4.5 ohms also it will be 0.5 amps only, but only here it's going to get split, here and here it's going to get split, and this ratio, it's in the ratio 1:2. The resistors are in the ratio 1:2. The current will be in the ratio 2:1. It's very simple. Okay, if the resistors are in the ratio 3/6 is nothing but 1/2, the current will be in the ratio 2:1. The current and the resistors are inversely proportional. So the current through this and this will be in the ratio 2:1, and so 0.5 amps is the total current, right? It is therefore the total traction is 3. Okay, the total fraction is 3, and so it is 2 by 3 of 0.5 and a 1 by 3 of a 0.5. That's how the current will get split. Okay, so then it is 1 by 3 in the first case and a 0.5 by 3, which is 0.3 ones are 3, 6 3s are 18, something like that. So that will be the respective currents. So do you understand what I am saying? It's a very very important point. I hope you can see what I am saying. I will tell you this once again. Since the resistors here is in the ratio 3:6, the current will be in the ratio 6:3. A 1 by 2 ratio will become 2:1 in terms of current. So 2:1, when the current is breaking it in the ratio 2:1, it's 2 by 3 of the total current, which is 0.5, will flow in the on the up wing, and a 1 by 3 of a 0.5 will flow in the lower wing. So that is 5 to 10, 1 by 3, and this is half of it basically, is it? So it's 1 by 6 amps. So you understand that this is 1 by 3 amps on the top wire and it's 1 by 6 amps at the bottom wire. So it's such a beautiful sum where one is getting charged, another is getting discharged. Was there any use in finding the V, the terminal potential difference? No, the question has not, they have not even asked to find the terminal potential difference, but there is a board question wherein they will ask you to find the terminal potential difference. So it is a must that you know the terminal potential difference, otherwise the approach of the sum is very very simple. Okay, so let's go to next sum. So then I'll go next to sum for the day. I have not, these are not Kirchhoff's loop rule. So you understand where to use Kirchhoff loop rule, where you don't have to. So these are not Kirchhoff loop rule sum, these are normal electric current sums, where I'll upload it as EMF voltage numericals, okay, EMF terminal potential difference numericals. Okay, so let's go to next sum. I would like to do only specific sums. I don't want to end up doing everything here. So then take page, after that you can take page number 3.72 in my Aurora. I don't know what is it. It's example 133, wherein there are 4 identical cells. There's a graph given, okay, 4 identical cells, which means there's a 1 cell, 2 cell, 3 cell and 4 cell. It's like this. That's what it means, 4 identical cells. 4 identical cells of internal resistance small r are connected in series to variable resistors. So you can add E1 plus E2 plus E3. So then it's correct, the graph will be E1 plus E2 plus E3 plus E4. Each of, they have given in the graph, this is 5.6, this is 1.4, this is 2.8 and this is 4.2. And they have given this to be 0.5, a 1.0, a 1.5 and a 2, and the graph is connecting this and this. So this is a V versus V in volts versus I in ampere, a VA graph, from which you know this is minus R. Everybody knows this is V is equal to E minus IR. That's the formula where it's like Y is equal to mx plus V format, where minus R will be the slope. Yeah, so what are the question? What is the EMF of each cell? The total, can you see the total is 5.6 and it's made up of 4 batteries. So 5.6 by 4 will be 4 ones are 4, 4 fours are 16. So EMF of one cell is 1.4 volt. So EMF of each cell is therefore 1.4 volts. If you look at the y-axis, you have the total voltage divided by 4 because there are 4 cells is given in the question. Second, for what value, for what current from the cell does maximum power dissipation occur? Okay, for what current there's maximum power dissipation? Okay, first of all let's find, okay, let's do one thing. Let's find the third part of the question is to find the internal resistance. Let's do that, small r. You know, it's just the slope which is opposite by adjacent, which is 5.6 by 2. Very simple. So let's do a 5.6 is the opposite side by 2, which is 2.8 ohms. 5.6 by 2, which is 2.8. Yeah, 2.8 ohms is the total internal resistance. I gave it in the exam, but I never taught you this. Okay, please, there is some other detail which we have left out in the test. But the question is to find the internal resistance of each cell. Then each cell they connected in series, so each cell means 2.8 by 4, which is 0.74, so 28 ohms. That will be the internal resistance of each cell, and that is where we will miss out. I gave you marks in the exam for writing 2.8, but the question is to find the internal resistance of each cell. Very important. Now coming to the second question, for what value of current, this power dissipation maximum? When the current is maximum, power dissipation is maximum, because P is equal to I square R. Okay, so then when current is maximum, obviously power dissipation is maximum. For the maximum value of the current, I is equal to, what is total EMF? They are all connected in series only. When all the 4 batteries are connected in series, it will be 4E by the total resistance. Total resistance. You have to connect this to an external resistor. So you have to connect this to an external resistor. So there's each one has got internal resistance also and an external resistance also. The external resistor should have the same value of the equivalent internal resistance, which is 4R, so that the current can be maximum. So then the 4R is the series resistance, all of them together, and then this 4R, and therefore this is the condition. The condition for current to be maximum in any circuit is the external resistor has to be equal to equivalent internal resistance. Equivalent internal resistance is 4R. So capital R, 4R plus capital R, which is 4R plus 4R. So 4E by 8R. So then it's 4 by 2R. Okay, 4 and this get cancelled. So E by 2R is the answer, and E is the EMF of one battery. EMF of one battery is 1.4 by 2 into R of one cell, internal resistance 0.7, which will give you 1 amp. Again, such a beautiful sum. But this has come, can you imagine, this has come for board exam, but very old paper, very old paper, because when it is connected in parallel, a small capital R should be equal to NR by M. When connected in series, the capital R should be equal to just NR. This is the condition for the external resistors value should be equal to equivalent internal resistance in parallel and equivalent internal resistance in series for the current to be maximum. This condition is something you need to have memorized. Okay, so that's important. And then something is happening. Okay.